Hello, everybody. So we've done all the theory about hypothesis testing, and we've looked at how to do a hypothesis test for a proportion, and that was a one proportion Z test. Now we're going to talk about testing for means out of one sample. And the big change is that instead of a Z test, it's going to be a T test about a population mean. And so we're going to be talking about that, and we'll also talk a little bit about, and then not today's video, but the next video, paired data and reviewing more of this. So the big thing here is that P we use the Z distribution because it's approximately normal. But when we're taking a sample and we're looking at the mean, the sampling distribution's standard deviation is determined by the standard deviation of the population we're sampling from. So when we take a sample, we have to estimate it with the, right, so just real quick, so that was the standard deviation of the sampling distribution. The problem being is that we don't know this, and so we're estimating it with this from our sample, which means we have to use a T distribution. And so once again, we have to check the conditions. Random and independence are the exact same as they were for the proportion procedure and exactly the same as they've been for a while. The big one is normality, and once again we have to check normality according to one of three conditions. If n is less than 15, the sample data must appear to be normal or at least roughly symmetric, a single peak, no outliers. You will need to show a graph. Between 15 and 30, sample data, no outliers or no strong skewness. Once again, you will need to show a graph. If we're over than 30, then CLT has kicked in and we're in good shape. So let's look at it. Let's create one. Let's do a test for means. A classic rock radio station claims to play an average of 50 minutes of music every week. However, every time you turn to the station, it seems like there's a commercial playing. To investigate their claim, you randomly select 12 different hours during the week and record what the radio station plays in each of the 12 hours. Here are the number of minutes in each of these hours. And so this is our data set. And so if we, let's just see, the big thing is, I'll come back maybe. So if we were to put all this data into our calculator, or we just find the average, we'd find that the average is 47.916, and that the standard deviation is 2.811. And so the question is this difference big enough? And this is clearly below the 50. But is it enough below the 50 that we can say, aha, you, sir, are not telling the truth? Oh, one more piece of information. Our sample size is 12. Now, with the sample size of 12, we're going to have to check our conditions for normality. Also, we're going to need to set up our null hypotheses. So our null hypothesis is mu equals 50, and our alternative hypothesis is mu is less than 50, where mu is the true minutes of the true mean minutes of music played each hour. So that would be our null, and we defined our variable. So then, check the conditions for carrying out a significance test of the company's claim that it plays at least 50 minutes of average. So we could either do a dot plot, we could do a box whisker plot, or we could do a normal probability plot. And all of these are okay. The box plot is roughly symmetric with no outliers. The normal probability plot is more or less linear. The box plot is, it's not quite symmetric, but it's not wildly skewed either. We randomly selected the hours. There are more than 100 hours of music played during the week. So once again, this is what I said earlier, is that the standard deviation of the sampling distribution uses sigma, and we don't have that, so we have to use a t-distribution. And the t-distribution will have n minus 1 degrees of freedom. So in our example, we're going to be using t11. And so we would plug in our values here. So t11 is going, degrees of freedom equals 11, is going to be the x bar, which we said was 47.916, I really should say 7, minus 50, all over 2.811 divided by the square root of 12. And so here's what we had just said, our null hypothesis, our test statistic. They rounded a little bit more than I did. And so we will get a t-value of negative 2.59. And so you would go to table B and you'd look up 11 degrees of freedom and you would find where your value was on the table. And it's a little tricky, and we'll go over this in a second, but you would see it's between 0.01 and 0.02. So we know our p-value is in there. So we know that p-value is less than 0.02 but greater than 0.01. And so we can use and I'll teach you in class how to use the TI-84, not the 89, and the t-test in class to get an exact p-value out of this, not an approximate one. But we'll do that in class. And this is just more about using the table. And you can read through this, and you can go to the back of your book, and you can do this. The key is to always be conservative. So you're always going to round down if you're over 30 degrees of freedom to the lower value. So if you had 38, if you had like 44, if your sample size was 44, you would use the 40 row of the table. And then you just search for your p-value between two things, and then that's where you know your p-value is. It only shows positive values of t. If you get a negative value, you just do the absolute value of it because the diagram is symmetric. But once again, I'm going to go over in class on how to get these values from your calculator. So here's like an example of using the table. Suppose you were performing a t-test of the null hypothesis mu equals 5 versus the alternative mu does not equal 5 based on a sample size of n equals 37, and you get a t of 3.17. So that means you're going to use this row, 30 degrees of freedom, because your degrees of freedom is 36. And we'd have to do the absolute value of 3.17. And here you go. Do the symmetry of the curve. The probability that t is less than negative 3.17 is the same as the probability that t is greater than. And so it would be right in here. And so we know our p-value is between 0.025 and 0.01, but because the null hypothesis is not equal, it's a two-sided test, and we have to double our values. So we know our p-value would be between 0.002 and 0.005. And this is where it's useful if you do things on the calculator, because when you put in your null, it will tell you whether it's double-sided or not. And then it will automatically do the calculations. And we're just going to do a bunch of these in class, but that's the basic procedure for setting up and doing a one-sample t-test for means. And remember, conditions have to be met. You can only use this test when the population distribution is normal or the sample is large and the population is at least 10 times as large as the sample. Conditions have to be met in order to use the test. Otherwise, it's meaningless. This is mainly going to be an in-class thing, so I will see you guys in class and be ready to go.